So I think that's a good thing. And yes, Lauren, I agree. Light, I think, is a very interesting thing, and we obviously are using light in many ways in our day-to-day life. So it's neat to see the physics behind it. And what we'll focus on today, though, before we truly get into the light part of the module, is just kind of the patterning that's happening. And we'll start with the pendulum as one of the items. The audio problems are only for Blackboard, and the setup wizard doesn't work. Oh, thanks, Ms. Shields. Yes, that would be my next piece of advice. Every computer is different, and Ms. Shields and I definitely don't have the tech support background. I know a lot of times tech support can know just off the top of their head what the issue is because of earlier experiences, which we definitely don't have. So just to give you an overview, and hopefully this is an optimistic look at the fact that we really don't have a whole lot left for the course in general. Here's Module 6, and we are going to make it to this point right here. So really we're going to do what looks to be more than half of Module 6 before spring break. So your goal is to make it to this assignment here before we leave for spring break. And then when we get back from break, we'll just have that little bit of Module 6 and Module 7 to go. So I think that's a good thing. And just to give you a heads up on what's in the future here, if you remember, Module 3 wasn't as lab heavy. And I know during the holiday time, Thanksgiving and winter break, right before winter break, it was kind of nice that we didn't have a whole lot of big projects to do. And Module 7 is similar. There's a lot of very technical ideas in Module 7, but a lot of the assignments are very short. So if it is feeling like that looks like a lot of work to you, realize that a lot of the assignments are not nearly as time-consuming as some of the ones that we've been working on already. So I'm very optimistic that we'll all finish the semester well before the true deadline. And yeah, Isabella, I agree. Physics is almost coming to an end, so it is a little bit sad. We've been having a good year. So let's jump right into the equation sheet next. So Module 5 was a little shorter on equations. Module 6, we're kicking it back up a notch here with some more equations. And this page, I don't know if the one that I have on our site has all of the variables defined, but if it doesn't, you definitely can use this as a template. All the equation names are on here, as well as what each variable means and the common units that go with it. So if you haven't already been doing that for yourself on the equation sheets, that is definitely a strategy that I think is helpful. And it really helps jog your memory. If you come across an equation and you're like, oh, wait, what was that letter C? I've seen that before. The equation sheet can help you with that. So we really encourage you to become familiar with using those equation sheets. And I really think it makes everyone's life easier in the long run. So give it a try if you haven't. So here is our question of the day. What variables affect the period of a pendulum? And we're going to talk about some of those variables to make sure we're all considering the same variables. But I'm just curious, before we even talk about those variables, what do you think? And in case you're not familiar with a lot of everyday life pendulums, if anybody happens to have one of these fancy grandfather clocks, the swinging mechanism there is a pendulum, of course. A lot of fair rides. This one's probably doing more than just what a pendulum would do, but it spins a little, but it also swings. A Newton's cradle. I love those. Those are mesmerizing. And then I think this carnival ride's a pretty good one. A lot of times it's like a pirate ship, and it simply does swing back and forth. So any thoughts that come to mind, go ahead and put them in the white box there. What variables, and when I say the word variable, I really encourage you to think about what could you, if you set up a pendulum in your house, what variables could you really manipulate from trial to trial? And Helga, yeah, I'm kind of with you on that. I used to like them, and then I kind of phased into roller coasters. I like those better. The swingy, repetitive motion ones kind of give me a headache now. I don't know. And then it all depends, too, on if you've eaten already or not. It can get bad. Yes, Margaret, that's a good point. Yeah, your body is almost like a temporary pendulum there because you do have that fixed point. Miss Shields is not a fan of any of the rides. I'm still okay with roller coasters, but that may change as I get older. We'll see. Okay, I think this is a good start to the list, but it is not the exhaustive list. I have a couple more things that I want to introduce to you guys. And yes, Coral, you definitely are kind of a pendulum. I'm thinking like the uneven bars when you're swinging from one bar to another and getting ready to do that. And I know there's technical names for it. Yes. Perfect. So we see these in everyday life, and there are, at the very basic level, some relationships that we want to kind of picture and kind of keep in our mind here. So let's look at those terms. And this is one where the page is going to get messy. Please don't move anyone else's writing. But I'm hoping maybe if we do this neatly enough and make our matching lines, we want to go from the vocab here to the little circle dots that we have here and make a line. And I'm just going to turn you guys loose. Go ahead and make a line from the term to its description, and we'll see if it doesn't turn into math chaos. And we can overlap in our lines here, so everybody just jump right in, and there we go. That's what I'm hoping for. And if there are any lines that happen to go in the wrong spot, that's okay. We'll talk them through. Okay, I like that it's pretty clear to see what you guys are thinking here. So let's kind of talk these through a little bit. The period of the pendulum is the time it takes for one complete cycle. And we're going to look at visually what that cycle really consists of, because that could be open for interpretation. But if you just picture, I think, a swing at a playground. I don't know if anybody mentioned that one, but if you pull your friend back on the swing, you don't give them a push at all, but you just pull them back and get ready to release them. Watching that swing go back and forth would be the time factor of that would be the period. So it is measured in seconds. The mass, fun fact, is also called bob. Not sure the history behind that and why it's called bob, but you may come across that in reading somewhere, and don't be surprised. The mass attached to the pendulum string is bob, so say hi to Bob. That must be what it is, Ms. Shields. Yes, I didn't think about that as a verb. That makes more sense now. And it would be a mass measured in kilograms. All right, and then the cycle, like I said, is that path we're going to talk about. Amplitude is just another word for angle, and you've probably come across amplitude maybe in math class as well. So that angle that we're releasing from is a factor, and it would be measured in degrees. And then length. I think some of you mentioned that length would be the pretty obvious one. I could cut the string shorter. At a playground, I guess the length of the swing could be a different amount, affecting the length of the swing. So I think those are all probably pretty obvious once we have them all there in the list. Now what we want to do is look at the visuals that go with that. So I like this one because it kind of does a step-by-step so that we can really make sure we're all thinking of the same thing when we talk about a cycle. So if and again, this analogy of the swing at the playground is a good one too. We bring the bob back to a certain point where we're releasing it from. It swings through its center. It goes to the opposite extreme, and it has to swing back as well. So you really want to be cautious of that. Today in the measurements we do, I don't know that it will affect anything because we're measuring from the simulation, but if you were to, say, collect your own data and not stay to do the lab and you wanted to set up your own pendulum, you want to make sure you're allowing that pendulum to return before you stop your timer. So that is the cycle. And then, of course, the time it takes is that period value we're talking about. And I don't know if I mentioned it earlier, but it is the capital letter T. So I think that's a nice letter to go with it due to the fact that lowercase t was time, and period is really the time for that swing, but it's not just time, it's more specific. So we use a capital T there. So be aware of that. And then amplitude is simply that angle we're releasing from. What is our reference here? when we're measuring the angle, what are we measuring it to? Right, Coral, exactly, that vertical or that center. So, you know, just as easily we could have, maybe we have a table here or some kind of support, we could have measured from here to here, but instead we're measuring from the vertical, from that equilibrium position is another good word for it. So when you're looking at that angle, that's something to pay attention to. And then what we want to segue this into is the fact that if there isn't friction and we release this pendulum and we let it go, it will make this repeating pattern that's very predictable. And it will, what kind of function? Anybody remember from math? What kind of functions are we talking about here? Yes, very nice, sine and cosine. So it all depends on where we're starting it on the graph, and that's not information you'll have to carry with you, but it is neat to see that, oh, all these crazy graphs that they make us work on in algebra and Algebra 2 really do show up in real life, and they would be, in this case, what we call simple harmonic motion, which I think is a pretty nice, obvious name. It's very simple motion, but it's repeating or harmonic. So that is why the pendulum is in this module. All of the waves that we look at will have that repetitive nature to them too. So it's nice to start with like one example we could actually put our hands on if we wanted to put this pendulum together ourselves. So we're just about ready for time to break into groups. I do have a couple demos and intros that I want to share with you, but I am going to change the polling. So let me see here if I can make it work. So if you'd like to, and I switched it up, I guess this time. A is partner this time. B is if you'd like to work on your own. C is you're going to stay for the demo, but after that you'll probably leave. And D, other DBA. I meant to put that there. Okay, so the way we're going to start this as you're thinking about your plans for the lab today is to make a hypothesis. So what does it mean to make a hypothesis? Right, Coral, exactly. We're just kind of using what we know to say, well, this is what we think is going to happen, and at the end it's kind of nice to say, oh, yay, I was right on, or, oh, wow, I learned something today. So either way, the hypothesis does not count against you if you're wrong, as you probably already know, but it's nice to kind of tap into that prior knowledge and see what we can make as a prediction. So we've already talked about the fact that mass, amplitude, and length are going to be our three variables that we'll test. But of course, if we're truly doing an experiment, we're not going to have, let's say, 6 different pendulums with different masses, different angles, and different lengths. It's going to be really hard to say, oh, wait, that mattered, that didn't, and it would be a very confusing process. So what we want to do is just focus on one. We're going to change the mass of 2 pendulums, have one be light, one be heavier, and see if that affects the period of the pendulum. And what I want you to do is guess, well, do you think it's going to cause the pendulum to take a longer amount of time to swing back and forth? Do you think it will fall more quickly and it will take less time? Or do you think it's not a factor and the pendulums will stay the same? So what I want you to kind of play in your mind is really setting up 2 pendulums. We would have one over here with its bob, one over here with its bob, and the only difference would be that one has a larger mass. So maybe I could make this one look like this. And if you were to set this up yourself, which I did this morning, simply adding some extra washers, using 1 washer, let's say on the right one, and 4 on the left one. We would bring both of these back to the same angle. The strings would be the same length. We'd let them go, and we'd look to see if mass is a factor. So kind of play those scenarios in your mind, and what I want us to do as a class is see if we can come up with a class hypothesis. If we are very scattered and we clearly don't agree at all, that's okay. You'll be able to write your own hypothesis as a smaller group in your breakout room. But I'm curious to see as a whole how we feel about this. So use either one of the icons in the little picture tool or just your pen to make a tally mark in whichever box you think is appropriate. So for example, if I think mass, making the pendulum more massive will increase the time it takes to swing, I'd put a tally here. If I think it will cause the pendulum to swing faster and the time would decrease, I'd put a tally here. Or if I think it's not a factor, I of course would put a tally there. So you're making one tally mark in each of the rows based on what you think will happen. And you can go ahead and do that now. Oh, and yeah, that's why no one's written on the board yet. I'm like, somebody's going to start here soon. Well, there you go. Now you have the privilege. Go ahead and make your tally marks. Some of us are much neater tally mark makers than others, but I'm okay with that. It's interesting to see what we think prior to the experiment. This is fun. Okay, so I would say we all agree so far that changing the amplitude will make the pendulum take longer to complete that arc. It looks like mass were a little debatable here, and length maybe a little bit debatable as well. So I'm going to leave it up to you guys in your breakout groups to rediscuss this point, and you can fill in your hypothesis as your small group. If we're writing it right now, we could say if mass is increased, the period should increase as well. Could be a way I word it. Or it decreases or it stays the same. So you'd be filling in that blank. If amplitude is increased, the period increases. And if length is increased, it looks like we're 50-50 there. Well, not quite. Maybe 80-20. But you can fill those blanks in your breakout room. So now that we've thought about it, let's look at what the actual experiment, oh, you know what? I didn't have a slide for that. Okay, so let's go, I guess these would be where we're going to, yeah, this is what we'll have to do. Okay, so I think what I'll do is just improvise here a little bit. The first test we're going to do is mass. So this morning, I wanted to set up a pendulum of my own. I search the internet from time to time, pretty much every year that I teach this lesson, and I've never really found a video that I like the best. So I decided to make one of my own, and some of you that are subscribed to the YouTube channel may have gotten an alert of it. So I did load it this morning, and I'm going to share it with you guys now, and it's only 2 minutes, so I'd like you to watch it now, and then we can discuss to see maybe what our next proper steps will be. So give me a second here to get this up on the screen. So go ahead and share some observations in the chat box if you don't want to take the mic. So Sierra says the shorter length made it swing back faster. That's a great observation. So that's one thing we can say. And maybe we should just add those to the box, to the screen down here. So let's put some of those statements in here. Shorter length decreases the period. What about, let's go back to mass. What did we see happen? I'm just going to add a tiny little row here for some observations. That's what we're looking for, Anna. Exactly. If you think back to the mass one, and of course you can watch this again, but both the 4-washer mass and the 1-washer mass reached my hands at the same time. So that tells me really that the period was not affected by the more massive pendulum. So in other words, mass was not a factor, right? And yes, so we can put the smiley face there for mass. They reached my hands at the same time, which forces us to say that the period would stay the same. And then amplitude. That's where I had one at a high angle and one at a lower angle. Did one get back to my hands before the other, or was it the same? And here's a copy of the video again if you want to look back at those, because I know I'm already whistling the background song. And I think it'll vary a little bit from trial to trial, but really they reached my hands at nearly exactly the same time too. Maybe not as perfectly as math, but not different enough for the difference in angle. So yep, it should be stays the same as well. So you can watch that part again. Both reached back at the same time is what we should have seen there. So Isabella, did you have a question? So where the smileys are. I'm writing observations over here just off to the side of what we saw, and then the smileys are what really happened. And now let's verify the last one here. So if the length is increased, if we're making that pendulum longer, which I think in the video was the one on the left, what happened there? The shorter was faster, right. So we have to be careful of the wording here. What is this statement saying? It's saying if length is increased, the period of the pendulum will. So if I focus on that longer one, the longer pendulum was slower. So does that mean there's an increase in time or a decrease in time? Right. So we can both be right, but that would also mean that we worded it in the opposite way. So we really want to bring that smiley face. Whoever put the smiley face there, if you could slide it over, it doesn't look like it's moving for me. Or we can just cross that smiley face out. We really need one in the increase column there. There we go. And we'll cross out the smiley face so we don't confuse ourselves. Okay, thank you. Okay, so this is kind of a nice conclusion in itself, knowing that, well, length is really the only thing that mattered. But what we want to look at now is kind of that next level. Well, if I double the length of the pendulum, is that also going to double the time it takes? We don't know for sure if it's truly a linear relationship. So that's really going to be your responsibility in the breakout rooms or later when you do the remainder of the lab if you choose not to stay. So let's look at how that will play out. So step 2, it looks like someone already did that for us. Oh, and actually that was our hypothesis. This is the actual test. So we're going to change that. You'll fill in this. And this was just a set of data to show the same thing. So notice in the simulation, let's see, what are we changing here? The mass. The mass is right here. One was 250 and the other was 50. And the period of the pendulum would be right at the peak. So if we look at the peak of both of these graphs, they were both at 2.1. So this is just really a graphical way, simulation-based, of looking at that same thing. And then with amplitude, same thing here. So really step 2 and 3, all you're doing is filling in this bottom, filling in the rest of the sentence. And yes, the template has this similar fashion, so you'll just carry on with the remaining step. The last thing you'll do is use the second video I have for you guys to collect the data so we can really see what kind of relationship is here. What we're really going to do is kind of derive the true pendulum equation at a very basic level. If you have a graphing program you like, you can also put the data in a graphing program and paste that graph on the screen as opposed to graphing it by hand. Either way is fine. And then a couple questions to answer. So we're just about ready to Move into breakout groups. And I think the last thing I want to share is just up here in the corner here. This is the equation that we end up getting for the period of the pendulum. So a little spoiler alert, this is what we'll end up working with. And I think the variable should be obvious. T, of course, is the period of the pendulum. Capital L would be what? I should see the chat box exploding. There we go. A slow explosion. The only variable that mattered, right? Mass is not a factor. Amplitude's not a factor. So those aren't in the equation. And then what's G? Yes, thank you, Sarah. There is a special number, one of very few, that's probably worth putting to memory. Yes, you guys have got it. So 9.8 will there. Technically, it's a negative vector, but we drop that here because we're not taking any square roots of negative numbers. So simply a 9.8 will go in there. So all you're going to do once you've completed your data collection and your graph is determine, well, was that graph really linear or do you see a parabola there? You're just circling one or the other. And then you'll work with your partners to calculate the unknown. So if I don't know the length of the pendulum, but I do know the period, I'd be entering in the 1 and doing the algebra to solve. So I will admit this equation is a little messy to solve, but that can be a time where if you get stuck with the algebra, you rely on your partners, or you raise your hand and Ms. Shields and I can come help. So you should each be doing one calculation if you are a group of 3. Does anybody have any questions before we break into groups? Oh, and of course, a conclusion is the last step. That's the very final slide, I believe. Yep. So I will start making the breakout rooms, and in case you've forgotten your choices, they are right here. Yes, Helga. Period is in seconds. And our lengths should be in meters for it to all work out properly. Okay, I will start making those breakout groups, and if you haven't already made your decision, please do so now.